Lesson for today is pre-stressed concrete. At the end of the session, students should be able to number 1, understand the principle of pre-stressed concrete. Number 2, determine type of pre-stressed concrete. What is pre-stressed concrete? Pre-stressed concrete is a form of concrete used in construction. It is substantially pre-stressed or compressed during production in a manner that strengthens it against tensile forces which will exist when in service. This compression is produced by the tensioning of high-strength tendons located within or adjacent to the concrete and is done to improve the performance of the concrete in service. The internal stresses are induced to counteract external stresses. In 1904, Freyssinet attempted to introduce permanent acting force in concrete to resist elastic forces under loads and was named pre-stressing. Pre-stressed concrete is a structural material that allows for predetermined engineering stresses to be placed in members to counteract the stresses that occur when they are subjected to loading. It combines the high-strength compressive properties of concrete with the high tensile strength of steel. The history of the use of concrete is marked by a succession of invention, innovation, and patents. In 1848, Joseph Louis Lambert built a cement boat using wire covered in cement. The world owed the inventions of reinforced concrete to Joseph Monnier. Between 1867 and 1891, he registered a number of patents for an iron and cement system for manufacturing flower pots, pipes, and water tanks. The first design rules for reinforced concrete appeared in Switzerland in 1904. In 1929, Eugene Freyssinet revolutionized the world of construction when he invented pre-stressed concrete. He used high tensile steel wires with ultimate strength as high as 1,725 megapascal and yield stress over 1,240 megapascal. In 1939, he developed conical wedges for an anchorage for post-tensioning and developed double-acting jacks. He is often referred to as the father of pre-stressed concrete. In 1938, Hoyer E. from Germany developed long-line pre-tensioning method. And in 1940, Magnell G. from Belgium developed an anchoring system for post-tensioning using flat wedges. Concrete itself is strong in compression and weak in tension. Let's say a concrete beam is applied with load. The concrete beam stands to bend. The upper part of the beam is in compression, while the bottom part of the beam is in tension. Because of concrete is strong in compression, the upper part of the concrete beam requires no support. However, due to weak in tension, tensile strength of concrete is neglected. Therefore, the bottom part of the concrete beam requires support. Since steel is strong in tension, steel is used as support in the bottom part of the concrete beam. Whenever cracks occur in the bottom part of the concrete beam, when applied with load due to tensile force, the steel holds the concrete beam from fail. In ordinary reinforced concrete, stresses are carried by the steel reinforcement, whereas pre-stressed concrete supports the load by induced stresses throughout the entire structural element. This makes it more resistant to shock and vibration than ordinary concrete and able to form long, thin structure with much smaller sectional areas to support equivalent loads. Pre-stressed concrete is now commonly used for components such as floor beams, piles, and railway sleepers, as well as structures such as bridges, water tanks, roofs, and runways. Generally, pre-stressed concrete is not necessary for columns and walls. However, it can be used economically for tall columns and high retaining walls with high bending stresses. The steel used for pre-stressing may be in the form of wire or tendons that can be grouped to form cables. However, solid bars may also be used. As a general rule, traditional reinforced concrete is the most economic method for a span of up to 6 meters. Pre-stressed concrete is more economical when spans are over 9 meters. Between 6 and 9 meters, the two options must be considered according to the particular requirement as to which is the most suitable option. Pre-stressed concrete has more capabilities compared to the traditional reinforced concrete. Pre-stressed concrete has high load-bearing capacity, less deflection when applied with load, more economic, high shock resisting ability, longer span, and less safe weight. Principle of pre-stressing. Pre-stressing is a method in which compression force is applied to the reinforced concrete section. The effect of pre-stressing is to reduce the tensile stress in the section to the point till the tensile stress is below the cracking stress. Thus, the concrete does not crack. It is then possible to treat concrete as an elastic material. The concrete can be visualized to have two compressive forces. Number 1, internal pre-stressing force. Number 2, external forces from dead load and live load. These two forces must counteract each other. The process of pre-stressed concrete can be either through pre-tensioning or post-tensioning. Compressive stresses are induced in pre-stressed concrete either by pre-tensioning or post-tensioning the steel reinforcement. Pre-tension is when tendons are tensioned before the concrete is placed. After the concrete hardens, the tension force is released. Post-tension is when tendons are tensioned after the concrete hardens. In pre-tensioning, the steel is stretched before the concrete is placed. High-strength steel tendons are placed between two abutments and stretched to 70 to 80% of their ultimate strength. Concrete is poured into molds around the tendons and allowed to cure. Once the concrete reaches the required strength, the stretching forces are released. As the steel reacts to regain its original strength, the tensile stresses are translated into a compressive strength in the concrete. Typical products for pre-tension concrete are roof slabs, piles, posts, bridge girders, wall panels, and railroad ties. This process involves the stressing of wires or cable by anchoring them at the end of a metal form, which may be up to 120 meters in length. Hydraulic jacks stress the wire as required, often adding 10% to accommodate creep and other pre-stress losses that may be incurred. Side molds are then fixed and the concrete placed around the tension wires. The concrete hardens and shrinks, gripping the steel along its length, transferring the tension from jacks to exert a compressive force in the concrete. Once the concrete has reached the desired strength, the tension wires are released from the jacks. A typical concrete strength of 28 Newton per millimeter square can be achieved by 24-hour steam curing, as well as using additive. To create shorter members, dividing plates can be placed at any point along the member, which, when removed, permit the cutting of the wires. In the pre-tensioning system, the tendons are first tensioned between rigid and anchor block cast on the ground mold type pre-tensioning bed prior to the casting of concrete in the mold. The tendons comprising individual wires or strands are stretched with constant, with tendon anchorage at one end and jack at the other. With the forms in the place, the concrete is cast around the stress tendon. This is the example of manufacturing process of pre-stressed railway sleepers. Number 1. The preparation of tendons. Number 2. Apply oil to mold to prevent direct contact between concrete and mold. Number 3. Lay tendons in the mold. Number 4. Tendons are stretched by jack. Number 5. Pour concrete in the mold. Number 6. After concrete cure and harden, tendons are released. Number 7. Concrete sleepers are removed. Number 8. Further curing process. And number 9. Sleepers are stored and ready to deliver. Post-tensioning. In post-tensioning, the steel is stretched after the concrete hardens. Concrete is cast around, but not in contact with unstretched steel. In many cases, ducts are formed in the concrete unit using thin wall steel forms. Once the concrete has hardened to the required strength, the steel tendons are inserted and stretched against the ends of the unit and anchored off externally, placing the concrete into compression. Post-tension concrete is used for cast-in-place concrete and for bridges, large girders, floor slabs, shells, roof, and pavements. This follows the reverse method to pre-tensioning, whereby the concrete member is cast and the pre-stressing occurs after the concrete is hardened. This method is often used where stressing is to be carried out on site after casting an in situ component, or where a series of precast concrete units are to be joined together to form the required member. The wires, cables, or bars may be positioned in the unit before concreting, but bonding to the concrete is prevented by using a flexible duct or rubber sheath, which is deflated and removed when the concrete has hardened. Stressing is carried out after the concrete has been cured by means of hydraulic jacks operating from one or both ends of the member. Due to the high local stresses at the anchorage position, it is common for a helical or spiral reinforcement to be included in the design. When the required stress has been reached, the wire or cables are anchored to maintain the pre-stress. The ends of the unit are sealed with cement mortar to prevent corrosion due to any entrapped moisture and to assist in stress distribution. Anchorage used in post-tensioning depend on whether the tendons are to be stressed individually or as a group. Most systems use a form of split cone wedges or jaws which act against a form of bearing or pressure plate. In post-tensioning, the concrete units are first cast by incorporating ducts or grooves to house the tendons. When the concrete attains sufficient strength, the high tensile wires are tensioned by means of jacks bearing on the end of the face of the member and anchored by wedges or nuts. The forces are transmitted to the concrete by means of an anchorage, and when the cable is curved through the radial pressure between the cable and the duct. The space between the tendons and the duct is generally crowded after the tensioning operation. Most of the commercially patented pre-stressing systems are based on the three principles of anchoring the tendon, such as number 1, wedge action producing a frictional grip on the wire. Number 2, direct bearing from the rivet or bolt heads formed at the end of the wire. And number 3, looping the wire around the concrete. The pre-stressing steel is made of single unit wire or cable combined with 2, 3 or 7 wires or cables to form a strand. A group of strands are combined to form a tendon. However, instead of wire, a tendon can be made up of single steel bar, which diameter is much larger than a wire. But wire is normally used for pre-stressing steel. This is an example of post-tensioning system used for a bridge. Hydraulic machine is used to provide tension force to the tendon. This is the anchor system used to lock the tendon after the tension force was applied. The anchor system comprises of bearing anchor, wedge plate, wedge, and duct. Tendon is a stretch element used in a concrete member of structure to impart pre-stress to the concrete. Anchorage is a device generally used to enable the tendon to impart and maintain pre-stress in the concrete. This is an example of post-tension system used for a concrete slab. The ducting for the tendon is provided during the fixings of reinforcement bar and formwork prior to concreting. Soon after the concrete slab was hardened, the tendon will be inserted and provided with tension force. Generally, pre-stressed concrete is divided into two systems. Number 1, pre-tensioning. Number 2, post-tensioning. Pre-tensioning use Hoyer system. Meanwhile, for post-tensioning, there are 4 systems such as number 1, Freyssinet system, number 2, Magnell system, number 3, Gifford-Udall system, and number 4, Lee-McCall system. For pre-tensioning, the Hoyer system is generally used for the productions on large scales of pre-tension structural element of the structure only. Such type of method consists of stretching the wires at greater distance apart. Then the concrete is poured so that many structural elements can be produced in a single line, and for that the shattering should be provided. Once the concrete is hardened, then the wires are cut or released. Also in one line, the remaining wires will be cut off. By this method, the pre-stress is transferred to the concrete structure as there is bond between the tendons and concrete. In the earlier days, pre-tensioning system was mostly used but nowadays the post-tensioning system is used, while for larger span, the pre-tensioning system is found to be uneconomical. For post-tensioning system, the main principle in the post-tensioning system is to introduce pre-stress in the concrete member casted earlier, and by tightening the tendons which are accommodated in the ducts which are formed while beam is casted. When the tendons are pulled and tightened with the help of check arrangement against the end of concrete element, then the required pre-stressing force is obtained suitably. Once the wires are stretched, then they are anchored in the stretched position against the end of concrete member with the help of wedging devices. The different wedging devices and arrangement of wires are available in the different systems. At the end of the member, the excessive bearing stresses are produced because of the anchoring devices which bear against the cracks. Therefore, additional reinforcement is provided in the member so that the local splitting and failure due to shear will be avoided. In the case of pre-tensioning method pre-stress, there is a compressive force in the concrete which is because of the bond between the concrete and steel wires. If the limited sizes of the concrete are to be produced as mass production, then this method is adopted economically, as the transporting bigger products and handling them is practically impossible and very costly. The economical length of the concrete member should is up to 20 meters if such type of pre-stressing is adopted. There is considerable difficulty occurs in the transporting of concrete members of longer than 20 meter length. There are many ways to do the stretching of pre-stressing wires in the method of post-tensioning once the concrete is hardened, such as: number 1. The cable may be accommodated inside the sheaths of pre-stressing before the placing of concrete. Number 2. The holes may be kept along the longitudinal directions of the concrete member so that the cables can be placed after hardening the concrete. Among the post-tensioning system, Freycinet system is introduced firstly of all other systems. High-tension steel wires of diameter varying from 5 mm to 8 mm, about 12 numbers, are properly arranged to form a group into a cable with a spiral spring inside. The spiral spring provides the means for appropriate clearance between the wires, and therefore it provides the channel which is cement grouted afterward. It is further used to assist to transfer the reaction into the concrete. This thing is properly enclosed in the thin metal steel. The anchorage system consists of a cylinder of good quality concrete and is provided with some corrugation on outside parts. This has a central hole and is provided with heavy circumferential reinforcement. These cylinders are then kept in proper position, and then the conical plugs are being pushed into the conical holes after cables are properly tightened. The central hole passing axially through the plug will permit cement grout injected in it. This is the way to put space between the wires which will be filled with cement grout. This arrangement will give an additional restraint against the problem of slipping of the tendons. Advantages of the Freycinet systems are: Securing wires is not the expensive process. The required force for stretching the wires can be obtained very quickly. The plugs, if placed in the concrete, then it so not project beyond the ends of the member. However, there are disadvantages of the Freycinet system, such as all the wires of cable should be stretched together in this system, and therefore the stresses in the wires developed may not be exactly the same. The greatest stretching force, which is applied in the range of 250 kN to 500 kN, and this may not sufficient in many cases. The jack arrangement used in the system are very heavy and expensive, therefore the practical difficulties are associated with it. From the above system, it is clear that the system for pre-tensioning, pre-stressing are different from the system used for post-tensioning system. Depending upon the situation and structural members, the pre-stressing system are appropriately decided and used. The advantages of pre-stressed concrete include: number 1, the inherent compressive strength of concrete is used to its fullest. Because concrete is good in compression, application of pre-stress causes all the concrete section to be in compression. Number 2, the special alloy steels used to form the pre-stressing tendons are used to their fullest. Because concrete is weak in tension, the pre-stressed tendon used has changed the bottom part of the concrete from tension to compression. Number 3, tension cracks are eliminated, reducing the risk of the steel components corroding. Because the bottom section of the concrete has changed from tension to compression, therefore no crack due to tension will happen. Number 4, shear stress are reduced. Because all section of the concrete now is in compression, failure due to shear is unlikely to happen. Number 5, for any given span and loading condition, a reduction in weight can be achieved from using a component with a smaller cross-section. Due to the application of pre-stress, the size of the concrete section could be reduced. Number 6, a composite member can be formed by joining individual precast concrete units together. Due to limitation of size, members or components could be joined to form a large or long section. The disadvantages of pre-stressed concrete include: number 1, a high degree of workmanship and control is required. Because of the process is complex from traditional concrete, therefore it requires skilled workmanship and proper control. Number 2, special alloy steels are more expensive than traditional steels used in reinforced concrete. Because of the tendons are made from wire to form strand, the cost may higher from the traditional concrete. Number 3, expensive equipment is needed and there are complex safety requirements. Extra equipment such as hydraulic jack is required to provide stress force to the tendon, and the tendon with force can cause injury to the worker if it is damaged. Because of the advantages of pre-stressed concrete system, they are suitable to be used for bridges, slab in buildings, water tank, concrete pile, thin shell structures, offshore platform, nuclear power plant, and repair and rehabilitation structure. The forces in the pre-stressed tendon may experience loss for both pre-tension and post-tension due to number 1, elastic shortening, number 2, anchorage slip, number 3, friction loss, number 4, creep and shrinkage of concrete, and number 5, relaxation of steel. Elastic shortening meaning that the length of the concrete section and pre-stressed steel having slight shortened due to the forces applied. When the tendons are cut and the pre-stressing force is transferred to the member, concrete undergoes immediate shortening due to pre-stress. Tendons also shortens by the same amount, which leads to the loss of pre-stress. The loss range is between 3 to 6%. The friction generated at the interface of concrete and steel during the stretching of a curved tendon in a post-tension member. The friction in the jacking anchoring system is generally small. More serious frictional loss occurs between the tendon and its surrounding material. Frictional loss occurs only in post-tension members. The loss due to friction does not occur in pre-tension members because there is no concrete during the stretching of the tendon. Friction is generated due to the curvature of tendon and vertical components of the pre-stressing force. Friction loss is not more than 2%. Friction loss is the summation of number 1, friction loss due to length effect, number 2, friction loss due to curvature effect. Length effect means if the profile of cable is linear, the loss will be due to straightening or stretching of the cables. Curvature effect means if the profile is curved, there will be loss in stress due to friction between tendon and the duct or between the tendon themselves. Therefore, to reduce the frictional losses, number 1, cable should pass through metal tubes. Number 2, the bend should be through as small angle as possible. Number 3, radius of curvature for bend should be large. Number 4, pre-stressing the wire from both ends. And number 5, over-tensioning the wires. In most post-tensioning systems, when the pre-stress force is transferred from jack to the anchoring ends, the wedges slips over a small distance. Loss of pre-stress is due to the consequent reduction in the length of the tendon. The amount of slip depends on the type of anchorage system as shown in the slide. Creep of concrete is defined as the increase in deformation with time under constant load. Due to the creep of concrete, the pre-stress in the tendon is reduced with time. Creep losses is in the range between 5 to 10%. The continuous deformation of concrete with time under sustained load. The factors affecting creep of concrete are number 1, age, number 2, applied stress level, number 3, density of concrete, number 4, cement content in concrete, number 5, water-cement ratio, number 6, relative humidity, and number 7, temperature. Creep is due to sustained or permanent loads only. Temporary loads are not considered in calculation of creep. Since the pre-stress may vary along the length of the member, an average value of the pre-stress is considered. Shrinkage of concrete is defined as the contraction due to loss of moisture. Due to shrinkage of concrete, the pre-stress in the tendon is reduced with time. Loss due to pre-tension is in between 4 to 6%. Meanwhile, loss due to post-tension is in between 3 to 4%. For pre-tension members, transfer commonly takes place after 14 hours after casting, and nearly all shrinkage takes place after that. For post-tension members, stressing may take place after 1 day or much later. Thus, a large percentage of shrinkage may already taken place by them. Relaxation of steel is defined as the decrease in stress with time under constant strain. Due to the relaxation of steel, the pre-stress in the tendon is reduced with time. Loss of relaxation of stress in steel is between 2 to 8%. Decrease in the stress is due to the fact that some of the initial elastic strain is transformed into inelastic strain under constant strain. Factors that affecting relaxation are number 1, time, number 2, initial stress, number 3, temperature, and number 4, type of steel. In conclusion, pre-tension loss comprises of loss due to creep plus elastic shortening plus shrinkage plus steel relaxation. Meanwhile, post-tension loss comprises of loss due to creep plus elastic shortening plus shrinkage plus steel relaxation plus anchorage slip plus friction. Loss of pre-stress is classified into two types. Number 1, immediate losses, which occur during pre-stressing of tendons and transfer of pre-stress to concrete member such as elastic shortening, friction, and anchorage slip. Number 2, time-dependent losses, which occur during service life of structure such as creep, shrinkage, and relaxation. The rule of thumb for losses. For average steel and concrete properties, the tabulated percentage may be taken as representative of the average losses. Overall, showing that pre-tensioning system lost more at 25% than the post-tensioning system at 20%. Now, let's watch video showing the examples of pre-tensioning system. Now, let's watch video showing the examples of post-tensioning system.
S&P Post-Tension Company Limited is a company operating business about designing, estimating price, and producing and installing post-tension, as well as giving advices about technical matters by proficient and highly experienced engineers and teams to respond satisfaction of customers with quality and punctuality. Step 1. Installing slab formwork. Step 2. Installing side formwork. Step 3. Placing lower reinforcement. Step 4. Installing anti-bursting reinforcement. Step 5. Placing lower reinforcement in column. Step 6. Installing punching shear reinforcement. Step 7. Determining position and placement of bar shear by profile height. Step 8. Placing tendon and tied with bar shear. Step 9. Installing anchorage and grout vent. Step 10. Placing top reinforcement and extra reinforcement. Step 11. Pouring concrete. Step 12. Removing side formwork. Step 13. Removing former. Step 14. Inserting block and jaws. Step 15. Stressing and measuring elongation. Step 16. Cutting strand end. Step 17. Filling socket with mortar. Step 18. Bleeding air for cleaning. Step 19. Grouting. Step 20. Removing scaffolds and back prop from excessive weight the floor can support. It starts from step 1 until the procedures are completed.
That's all for the lesson this time, and thank you.